Tonight, we're going to travel to the edge of time itself. Not the edge of the solar system, not the edge of our galaxy, the edge of everything that has ever existed. The farthest point that human eyes, aided by the most powerful instrument ever built, have ever reached. A place so distant that the light arriving from it left its source before the Earth existed, before the sun existed, before almost anything existed at all. And what we found there, what James Webb found there, has quietly shaken the foundations of everything we thought we understood about the universe and our place within it. Here is the thing most people don't realize. When scientists first turned Webb toward the oldest corners of the cosmos, they expected to find the universe in its infancy, small, chaotic, unformed, a rough sketch of what would one day become the structured, magnificent cosmos we inhabit now. Instead, they found something that should not have been there. Galaxies. Enormous, fully formed, brilliantly glowing galaxies, existing just a few 100 million years after the Big Bang, in a universe that had barely begun. Galaxies so massive, so organized, so impossibly mature that the researchers studying them used a word you don't often hear from scientists. They called it universe-breaking, because by everything we knew, by every model, every simulation, every equation built over decades of careful work, these galaxies could not exist, and yet there they were, burning at the edge of time, waiting for us to find them. By the end of tonight, you're going to understand exactly why this discovery changes everything, what it reveals about the birth of the cosmos, the nature of the first stars, the invisible forces shaping all of reality, and perhaps most strangely of all, what it quietly tells us about ourselves. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Somewhere out there, at a distance so vast it defies every analogy we have ever used to describe it, light is travelling toward us. It has been travelling for 13.5 billion years. It left its source before our sun existed, before our planet existed, before any of the atoms in your body had been assembled into the particular shape of a living, breathing, wandering human being. That light crossed the entirety of the observable universe, threading through voids and galaxy clusters and curtains of gas, and it arrived, finally, after all of that, at the golden mirror of the James Webb Space Telescope. And what that mirror revealed has quietly, permanently changed the way we understand the cosmos. I want you to sit with that for a moment. 13.5 billion years, a number so large it loses meaning the moment you try to hold it in your mind. So let me offer you something more concrete. The universe itself is only 13.8 billion years old. That means the light Webb captured left its source just 300 million years after the Big Bang. 300 million years sounds like a long time. In human terms, it is unimaginable. But in cosmic terms, in the full sweep of everything that has ever happened since the beginning of time, it is barely a breath. It is the universe as a newborn, as an infant, as something that had barely begun to exist. And yet from that newborn universe, Webb detected something that should not have been there. Something enormous, something structured, something that broke the models. Here is the thing most people do not realize about this discovery. It was not expected. Scientists did not point Webb at the farthest edge of the observable universe and expect to find mature, massive, fully formed galaxies burning in the dark. The models, the careful, peer-reviewed, decades-refined models of how the early universe evolved, predicted something much more modest. The early cosmos should have been a rough and turbulent place, filled with small clumps of gas and dark matter slowly pulling together under gravity, assembling themselves over hundreds of millions of years into the first primitive structures. That was the prediction. That was what every simulation, every calculation, every theoretical framework said we would find. Instead, Webb found galaxies, real ones, big ones, impossibly old ones. The word that started circulating among cosmologists was striking, not surprising, not unexpected, universe-breaking. That is what one researcher called it, and the phrase stuck because it was honest. These galaxies could not exist according to everything we knew. They were too big, too bright, too organized for the age of the universe at the time they were observed. It would be like traveling back in time to the earliest days of human civilization, to an era when we expected to find small nomadic tribes huddled around fires, and instead discovering fully built cities with architecture and roads and libraries. The timeline simply does not allow for it, and yet there they are, burning at the edge of time, indifferent to our confusion, waiting for us to find a new explanation. This is the mystery at the heart of what we're going to explore tonight. Not just the discovery itself, but everything it pulls along with it. Because when one piece of the cosmic puzzle turns out to be wrong, or at least incomplete, the reverberations travel outward in every direction. If massive galaxies can form in the first few 100 million years after the Big Bang, then our understanding of how dark matter behaves in the early universe may need revision. Our understanding of how the first stars formed, how quickly they lived and died, how rapidly the raw materials of the cosmos were assembled into structures, all of it comes into question. A single discovery, if it is strange enough, can rewrite entire chapters of science. And this one is strange enough. I find something deeply humbling about that. We built the most powerful space telescope in human history. We spent 30 years designing it, a decade constructing it, billions of dollars launching it into space, and then we held our breath while it unfolded. A process so delicate, so irreversible, that a single failure in any of the 344 individual mechanisms required to deploy, it would have rendered the entire mission lost. It worked. Perfectly. And the first thing it showed us, when we pointed it at the oldest light in the universe, was that we were wrong. Not wrong in a small correctable way, wrong in a foundational way. The universe has been forming galaxies faster and more dramatically than we ever imagined. And we are only beginning to understand what that means. There is something almost terrifying about it, if you let yourself feel it fully. We are a species that has spent centuries building tools to understand the cosmos. We have mapped the surface of Mars, measured the mass of black holes, decoded the structure of the atom. We have built equations that describe the behavior of the universe from the first fraction of a second after its birth. And then we built one more tool, a golden mirror floating in the cold dark 1,000,000 miles from home. And it looked back at the beginning of everything and showed us something we did not predict. Something we cannot yet fully explain. The universe, it turns out, has been keeping secrets from us, and it has been keeping them in the oldest, most distant light that exists. That light is what we are chasing tonight. We are going to follow it backward, all the way to the edge of time. We are going to try to understand what Webb actually found, what it means, and why it matters, not just to scientists, but to anyone who has ever looked up at the night sky and felt the particular mixture of wonder and unease that comes from realizing how small we are, and how vast and how strange everything else is. The signal at the edge of everything is not just a data point in a scientific paper. It is a message from the beginning of the universe, and it is telling us something we're only now beginning to learn how to hear. I want to tell you something about light that most people know in theory, but have never truly felt. Light is fast, extraordinarily, almost incomprehensibly fast. It travels at just under 300,000 kilometers every single second. In the time it takes you to blink, light has already traveled the distance from here to the moon and back. In 1 second, it could circle the entire Earth 7.5 times. We treat this speed as essentially instantaneous in our daily lives, because on human scales, it is. You flip on a lamp, and the room is immediately bright. There is no perceptible delay. But the universe is not built on human scales, and when you zoom out far enough, the speed of light stops being a convenience and starts being a constraint. A profound, strange, and almost poetic constraint. Here is what that constraint means in practice. When light leaves a source, a candle, a star, a galaxy, it begins a journey, and that journey takes time. The light from the sun takes about 8 minutes to reach your eyes. So when you look at the sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. That difference is trivial in most contexts, but it is real. The sun you see is a slightly younger sun than the one that actually exists at this moment. Now extend that principle outward. The nearest star beyond our sun, Proxima Centauri, is about 4.2 light years away. The light reaching us from that star left its surface 4.2 years ago. If Proxima Centauri were to suddenly vanish tonight, we would not know for more than 4 years. We would keep seeing it, keep measuring it, keep including it in our sky maps, and it would already be gone. Push further out, and the delay becomes staggering. The Andromeda Galaxy, our nearest large galactic neighbour, sits about 2.5 million light-years from Earth. When you look at Andromeda on a clear night, and you can see it with the naked eye, a faint smudge in the constellation of the same name, you're seeing light that left that galaxy 2.5 million years ago. At that time, our earliest human ancestors were just beginning to walk upright on the African savanna. The photons entering your eye tonight began their journey before Homo sapiens existed as a species. That is not a metaphor, that is physics. Every telescope, in this sense, is a time machine. The further it can see, the further back in time it reaches. This is the foundational idea that makes Webb so extraordinary, because Webb was not built merely to see farther than previous telescopes. It was built to see further back in time than any instrument in history. Its predecessor, the Hubble Space Telescope, could observe galaxies as they existed roughly 13 billion years ago, already remarkably ancient. But Webb pushes past that. It can detect light from galaxies as they existed just a few 100 million years after the Big Bang itself. We are talking about objects whose light has been travelling toward us for 13.5 billion years. Objects so distant, so ancient, that by the time their light arrives at Webb's mirror, it has been stretched by the expansion of the universe from visible wavelengths into infrared, into a form of light our human eyes cannot even see. Webb was designed specifically to detect that stretched, ancient, invisible light, and in doing so, it became humanity's first true window into the dawn of the cosmos. The concept of cosmic redshift is worth pausing on, because it is central to everything Webb does. Imagine you are standing on a train platform, and a train is moving away from you while sounding its horn. The sound waves stretch as the train moves away, and the pitch of the horn drops. It sounds lower, deeper, more drawn out. Light behaves similarly. As the universe expands, the space between galaxies stretches, and as that space stretches, it carries light along with it, pulling the wavelengths longer and longer. Blue light gets stretched toward red, ultraviolet gets stretched into visible, visible light gets stretched into infrared. The more the universe has expanded since the light was emitted, the more the light has been stretched, and the more it has been stretched, the older and more distant its source. Scientists measure this stretching with a number called redshift, written simply as z. The higher the z value, the further back in time the object exists. Webb has detected galaxies with redshift values above 14. That places them at a distance, and an age that Hubble could never reach. What this means practically is that when Webb captures an image of one of these ancient galaxies, it is not capturing a photograph of something that exists today. That galaxy, the exact object in the image, no longer exists in the form we see it. It has had 13.5 billion years to evolve. Its stars have lived and died. New stars have been born. It may have merged with other galaxies. It may have grown into something enormous, or it may have gone quiet, its star formation extinguished, its light dimmed. We have no way of knowing. We can only see the galaxy as it was, preserved in ancient light, a snapshot frozen at the moment those photons began their journey across the cosmos toward us. There is something deeply moving about that. We are not observing the universe as it is. We are observing the universe as it was. And the further we look, the further back we travel. I think about this sometimes on quiet nights. The light hitting your retina when you look at a distant star is ancient. It predates you by millions, sometimes billions of years. You're catching something that has been travelling since before human civilization, before the dinosaurs, before the formation of the Earth itself, and it ends its journey in your eye. In the particular moment of your particular life, there is something almost tender about that. The universe sends out these ancient messages, and we build instruments sensitive enough to receive them. Webb is the most sensitive receiver we have ever constructed, and the messages it is capturing right now from the edge of time are the oldest and strangest we have ever decoded. This is why the discovery we are building toward tonight is so significant. It is not just that Webb found something unexpected, it is that Webb found it at the very boundary of what is knowable, at the furthest edge of the look-back time available to us. To find something that breaks our models there, at the very beginning, means the confusion runs all the way back to the start, and that, more than anything else, is what makes this worth staying up for. The story of the James Webb Space Telescope does not begin with a launch, or a mirror, or a rocket. It begins with a question asked by a small group of astronomers in the late 1980s, a question so ambitious it seemed almost irresponsible at the time. What would it take, they asked, to build a telescope powerful enough to see the very first galaxies in the universe? Not the oldest galaxies Hubble could reach. The first ones. The ones that formed in the earliest light of the cosmos, before most of the universe had taken any shape at all. The answer they came up with was staggering. It would take decades. It would take billions of dollars. It would take engineering solutions that did not yet exist. And it would require placing the finished instrument in one of the most hostile and unreachable environments a human object had ever occupied. They decided to do it anyway. The formal study for what would become Webb began in 1996, nearly 8 years after that initial question was first seriously posed. From the very beginning, the scale of the ambition was clear, and so was the scale of the challenge. Hubble had been a relatively straightforward instrument in one important sense. It observed invisible and ultraviolet light, the kinds of light our eyes already understand, and it orbited close enough to Earth that astronauts could visit it for repairs. Webb would be fundamentally different. It would observe in infrared light, the stretched ancient light of the most distant galaxies. That requirement alone drove almost every other decision in the design. Infrared telescopes must be kept extraordinarily cold because heat, even the faint warmth of the telescope itself, produces infrared radiation that would drown out the faint signals from the early universe. The instrument had to be cold, colder than anything in Earth orbit could reliably achieve, and that meant it could not orbit the Earth at all. The solution was elegant and terrifying in equal measure. Webb would be sent to a point in space called the second Lagrange point, or L2, located approximately 1 million miles from Earth in the direction away from the Sun. At this precise location, the gravitational pulls of the Earth and Sun combine with the orbital dynamics of the system to create a kind of gravitational equilibrium, a stable parking spot where Webb could orbit the Sun in lockstep with the Earth, always keeping the same face toward the warmth and the same face toward the cold dark of deep space. On the sunward side, a massive sunshield the size of a tennis court would block the light and heat of the Sun, Earth and Moon simultaneously. On the shadowed side, the telescope and its instruments would cool to minus 233 degrees Celsius, just 40 degrees above absolute zero. At that temperature, Webb's own thermal glow would be essentially silent, and the faint infrared whispers of the ancient universe could finally be heard. The sunshield alone was an engineering marvel that took years to design and test. It is made of 5 thin layers of a material called capton, each coated with aluminum, and the outermost layer also coated with silicon. Each layer intercepts and radiates away heat before it can reach the next. The temperature difference between the sun-facing side of the outermost layer and the telescope side of the innermost layer is roughly 300 degrees Celsius, and all of that thermal insulation is achieved by 5 sheets of material, each thinner than a human hair. Spread across an area the size of a tennis court, folded into a package small enough to fit inside a rocket fairing, and designed to unfold reliably in the vacuum of space with no possibility of human assistance. No astronaut could ever reach Webb to fix it. Whatever happened after launch happened permanently. The primary mirror is perhaps the most visually iconic element of the telescope, and for good reason. It consists of 18 hexagonal segments, each made of beryllium, a lightweight, extremely rigid metal that holds its shape precisely even at cryogenic temperatures, and coated with a microscopically thin layer of gold. Gold, because gold reflects infrared light with extraordinary efficiency. Each segment is about 1.32 meters across, and together they form a primary mirror 6.5 meters in diameter, with a total light collecting area of about 25 square meters. For comparison, Hubble's mirror is 2.4 meters across. Webb's mirror collects roughly 6 times more light. That difference, translated into astronomical terms, means Webb can see objects roughly 100 times fainter than Hubble could. It can reach 100 times deeper into the darkness, 100 times further back in time, but a mirror that large cannot fit inside any rocket as a single piece. The entire telescope had to be folded for launch and unfolded in space, a sequence of deployments so complex, so dependent on each step, succeeding before the next could begin, that engineers identified 344 individual single-point failures, 344 moments where, if a single mechanism did not perform exactly as designed, the mission would be over. There would be no repair mission, no second chance. The telescope would simply drift in space, a billion-dollar monument to what almost was. The pressure on every engineer, every technician, Every manager who had spent years or decades on the project was almost unimaginable, and on December the 25th, 2021, after more than 2 decades of delays and cost overruns and redesigns, Webb lifted off from the European Space Agency's launch facility in French Guiana aboard an Ariane 5 rocket. It worked. Every fold unfolded, every latch latched, every mirror segment aligned. The sunshield deployed in sequence, layer by layer, across the void. After 30 years, the eye that could see the beginning of the universe had opened. I want you to feel the weight of what that represents. This was not the work of a single genius, or a single nation, or a single decade. It was the accumulated effort of thousands of engineers, scientists, programmers, and administrators across 3 space agencies, NASA, the European Space Agency, and the Canadian Space Agency, working across 30 years, surviving budget cuts and political pressure, and the slow grinding anxiety of knowing that a single failure would erase everything. They built something that had never existed before, to answer questions that had never been answerable before, and they sent it 1,000,000 miles from home with no possibility of rescue. And when Webb sent back its first images, the deepest, sharpest, most detailed views of the early universe ever captured, the world held its breath, because what we saw was not what we expected, and everything we thought we knew about the beginning of time started very quietly to come apart. To understand what Webb found, you first need to understand what it was looking for, and to understand that, you need to go back, all the way back, not to the formation of Earth, not to the birth of our sun, not even to the formation of the Milky Way. You need to go back to a moment so extreme, so alien to anything in our ordinary experience, that the very words we use to describe it feel inadequate. You need to go back to the beginning of time itself, to the first moment, to the instant when everything that exists, every atom, every galaxy, every particle of light, every thought ever thought, emerged from a single point of unimaginable energy and began its long, slow expansion into what we now call the universe. The Big Bang was not an explosion in the conventional sense. It was not a bomb detonating inside an existing space, sending debris flying outward into a surrounding void. There was no surrounding void. There was no space outside it. The Big Bang was the creation of space itself, the beginning of space, time, energy, and matter all at once, in a single event whose cause, if it had a cause, remains entirely beyond our current ability to know. In the first fraction of a second, in intervals so small they require scientific notation to write, the universe was a place of almost incomprehensible heat and density, temperatures measured in trillions of degrees, all of reality compressed into a volume smaller than a proton. The laws of physics as we understand them barely apply. This is the frontier where our equations break down and where humility is the only honest response. As the universe expanded, it cooled. This is a principle that applies to any expanding gas. Stretch it out and it loses heat. In the first 3 minutes, the temperature dropped enough for the first atomic nuclei to form, protons and neutrons locking together under the strong nuclear force to create the nuclei of hydrogen and helium, the 2 simplest and most abundant elements in the cosmos. But the universe was still far too hot and dense for electrons to attach to those nuclei and form complete atoms. The entire cosmos was a plasma, a thick, opaque fog of charged particles through which light could not travel freely. The universe was dark in the most literal sense. Not dark because there were no sources of light, but dark because even the light that existed could not move. It was trapped, scattered endlessly in every direction by the dense plasma surrounding it. This continued for approximately 380,000 years, and then something changed. The universe had expanded and cooled enough that electrons could finally combine with nuclei to form the first neutral atoms, a process cosmologists call recombination. In a remarkably short window of time, the fog cleared, the plasma became transparent, and for the first time in the history of the universe, light could travel freely through space. That moment of clearing released a flash of light that has been traveling outward in every direction ever since, stretched by the expansion of the universe into microwave radiation. We can still detect it today. It surrounds us on all sides, a faint cold glow at a temperature of just 2.7 degrees above absolute zero. We call it the cosmic microwave background, and it is the oldest light in the universe, a photograph of the cosmos when it was only 380,000 years old. But after recombination came a period that astronomers refer to, with quiet poetry, as the Cosmic Dark Ages. The universe was now transparent, but there was almost nothing in it to produce new light. The first atoms had formed, spread in a vast and nearly uniform cloud of hydrogen and helium gas, slowly cooling, slowly gravitating together under the influence of dark matter into the first faint structures. There were no stars yet, no galaxies, no supernovae, no planets, just gas. Vast, cold, dark, slowly stirring gas, pulled here and there by the invisible scaffolding of dark matter into filaments and clumps, like foam forming on the surface of a slow tide. The universe was quiet in a way it has never been since. For perhaps 100 to 200 million years after the Big Bang, there was no visible light anywhere in the cosmos. None at all. And then, from within those slowly condensing clouds of gas, the first stars were born. We call them population 3 stars, and they were unlike anything that exists today. They formed from gas that contained only hydrogen, helium, and the tiniest trace of lithium, the only elements that existed at that point. No carbon, no oxygen, no iron, no of the heavier elements that give modern stars and their planetary systems their complexity and richness. These first stars were enormous by necessity. Some estimates suggest they could have been hundreds, or even 1,000 times more massive than our Sun. Their cores burned at extraordinary temperatures, fusing hydrogen and helium at a ferocious rate. They lived fast and died violently, often in massive explosions called supernovae, seeding the surrounding gas with the first heavier elements ever produced in the cosmos. They were the universe's first factories, the first forges, and their light, blazing across the newly transparent cosmos, ended the Cosmic Dark Ages. This moment, when the first stars ignited and began to fill the universe with light, is called the Epoch of Rhionization, and it is one of the great transitions in cosmic history. This is the era that Webb was designed to study. The telescope's infrared vision, its extraordinary sensitivity, its massive golden mirror, all of it was engineered specifically to detect the faint red-shifted glow of these first structures emerging from the darkness. The first stars, the first galaxies, the first light after the long silence. Scientists expected to find the universe at this epoch in a state of early construction, rough, primitive, slowly assembling itself from small pieces. What they found instead stopped them in their tracks, because the universe, it turns out, did not take its time. It did not build slowly and carefully from simple beginnings. It built fast, shockingly, almost impossibly fast. And the galaxies Webb found burning at the edge of the observable universe are the evidence. Massive, luminous, fully formed structures existing at a time when, according to everything we knew, they simply should not have been there yet. In July of 2022, NASA released the first full-colour science images from the James Webb Space Telescope. The moment was broadcast live, covered by news organisations around the world, watched by millions of people who had followed the telescope's long journey from blueprint to launch to deployment, with something close to collective anxiety. The images were stunning in the way that only the genuinely new can be stunning. Not just beautiful, but disorienting. The deepest image showed a patch of sky roughly the size of a grain of sand held at arm's length, and within that tiny sliver of darkness, Webb had found thousands of galaxies. Thousands of entire galaxies, each containing hundreds of billions of stars, compressed into a region of sky so small you could cover it with a grain of sand. The universe, it turned out, was not mostly empty after all. Or rather, what looked like emptiness to every instrument before Webb was, when seen clearly for the first time, absolutely full. But the images that stopped scientists cold were not the ones released to the public with fanfare. They were the ones that emerged more quietly in the weeks and months that followed, as researchers began analysing Webb's data with careful, systematic attention. Because buried within the extraordinary depth of Webb's observations were objects that did not belong. Galaxies detected at redshifts so high, at distances so vast and ages so ancient, that their very existence presented a serious problem. Not a puzzle to be solved with a minor adjustment to existing models. A problem. A genuine, foundational, this changes things problem. The kind that makes theoretical physicists sit very still and reread their own papers with a new and uncomfortable suspicion. Here is the thing most people do not realize about galaxy formation. Under the standard model of cosmology, the lambda-cold dark matter model, which has been the dominant framework for understanding cosmic structure for several decades, galaxies do not form all at once. They assemble gradually, hierarchically over long stretches of time. Dark matter first collapses into structures called halos. Gas falls into those halos and begins to cool and condense. Stars form within the condensing gas. Those stars explode, seeding the surrounding medium with heavier elements. More gas falls in. More stars form. Small proto-galactic clumps merge with other clumps, pulled together by gravity over hundreds of millions of years, slowly building larger and larger structures. It is a patient process, a slow accumulation. Like a city growing from a village over centuries, not a metropolis appearing overnight. The galaxies Webb found in the earliest epoch of the universe do not look like villages, they look like cities. Enormous, luminous, structurally coherent galaxies, containing stellar masses that rival or even exceed those of the most massive galaxies in the modern universe, and doing so at a time when the universe was less than 5% of its current age. One study, published in the journal Nature in early 2023, identified 6 candidate galaxies observed between 500 million and 700 million years after the Big Bang, each with a stellar mass suggesting they had assembled billions of times the mass of our Sun in stars within an extraordinarily compressed window of time. The lead researcher described the findings with an honesty that is rare in scientific papers. She said simply that these galaxies should not exist, that if confirmed, they would break our understanding of how the early universe works. To understand why this is so startling, consider the analogy of building a skyscraper. Imagine you are told that skyscrapers take a minimum of 2 years to construct, because of the time needed to lay foundations, erect steel, pour concrete, install systems, and finish interiors. That timeline is not arbitrary. It is a physical constraint imposed by the nature of the materials and the process. Now imagine arriving at a construction site and finding a fully completed, occupied 100-story skyscraper that, according to the building permits, was started just 3 weeks ago. Your first instinct would not be wonder. It would be a deep suspicion that something is wrong with the permits, with your measurements, with your understanding of what it is even possible to build in 3 weeks. That is roughly the position cosmologists found themselves in when Webb's data began coming back. The galaxies existed, the measurements were checked and rechecked, and the timeline simply did not allow for them. The stellar masses involved are worth pausing on, because the numbers are the kind that require a moment of stillness to absorb. Our own Milky Way galaxy, which has had roughly 13 billion years to grow, contains an estimated mass of stars somewhere in the range of 50 billion to 100 billion times the mass of our Sun. That is the accumulated product of nearly the entire age of the universe. Some of the galaxies Webb detected in the early cosmos appear to contain stellar masses in a similar range, or in some cases even larger, compressed into a universe that had existed for only a few 100 million years. To build that many stars that quickly, using only the raw materials available in the young universe, would require star formation rates tens or even hundreds of times higher than anything we observe in the modern cosmos. The universe, in its infancy, would have had to be working at a pace that defies everything we thought we knew about how cosmic construction proceeds. What makes this particularly interesting, and particularly unnerving, is that it is not just 1 or 2 anomalous galaxies. It is a population, a consistent pattern across multiple independent observations, multiple research teams, multiple methods of analysis. This is not the kind of thing that gets explained away by a calibration error or a misidentified object. The signal is real, it is robust, and it is telling us something that our current best theory of the universe does not know how to explain. Some researchers have proposed modifications to the standard model, adjustments to how dark matter behaves in the early universe, or new physics governing the rate at which gas cools and collapses into stars. Others have suggested that the galaxies may appear more massive than they are because of light contributions from sources other than stars alone. The debate is active, serious, and unresolved. And that unresolved quality is, I think, the most honest and important thing about this discovery. Science does not always arrive with clean answers. Sometimes, the best times arguably, it arrives with a result that removes certainty instead of adding it. That forces you to sit with the discomfort of not knowing. Webb has done exactly that, It has looked at the beginning of the universe and found something we did not put there, something our models did not predict and cannot yet fully explain. And in doing so, it has reminded us that the cosmos is under no obligation to match our expectations. It simply is what it is. And what it is, it turns out, is stranger and more extravagant than we imagined. There is a particular kind of silence that falls over a room of scientists when data arrives that does not match the theory. It is not the silence of confusion exactly. It is something more careful than that. It is the silence of people who have spent years trusting a framework and who are now holding a result in their hands that the framework cannot accommodate, and who are deciding very slowly and very seriously whether the result is wrong or whether the framework is. That silence, in various forms, has been present in cosmology departments around the world since Webb began returning its early universe data. Because the galaxies Webb found did not just challenge the standard model of cosmology, they challenged it in the most uncomfortable place possible, at the very beginning, where the model's assumptions are oldest and most deeply embedded. The standard model of cosmology, formerly called lambda cold dark matter, often abbreviated as lambda CDM, is one of the most successful theoretical frameworks in the history of science. It describes the large-scale structure and evolution of the universe with remarkable precision. It correctly predicts the distribution of galaxies across cosmic time. It accounts for the patterns we observe in the cosmic microwave background. It explains the observed abundance of hydrogen and helium in the universe. It has been tested against an enormous range of observations and has passed those tests consistently for decades. This is not a fragile or speculative theory. It is a mature, well-supported, deeply trusted framework that cosmologists use every day to interpret everything they observe, which is precisely why the Webb results are so unsettling. Because a theory that works this well, over this many tests, over this many decades, does not break quietly. At the core of lambda CDM is a picture of how structure forms in the universe. It begins with dark matter, the invisible, gravitationally influential substance that makes up roughly 27% of the universe's total energy content. In the early universe, dark matter began to clump together into structures called halos, pulled by its own gravity against the smooth, expanding background of the cosmos. These halos then attracted ordinary matter, the gas that would eventually become stars and galaxies. The process was hierarchical. Small halos formed first, then merged into larger ones over time. Galaxies assembled inside these merging halos, growing slowly through a combination of star formation and galactic mergers. The key word in all of this is slowly. Lambda CDM is a model built on gradualism, on the patient accumulation of structure over long stretches of cosmic time. It does not have room for shortcuts. The galaxies Webb found at redshifts above 10, 11, 12, 13, existing when the universe was between 300 million and 500 million years old, do not look like the products of a slow and patient process. They look like the products of something that was working extraordinarily fast. Theorists who attempted to reproduce these galaxies in simulations found that, under standard lambda CDM assumptions, they simply could not. The simulations could not form enough stars quickly enough, in halos large enough, to produce galaxies of the observed mass within the available time. It was as if the universe had cheated, had somehow skipped several steps in the assembly process, and arrived at a finished product before the ingredients should have been ready. And when a simulation cannot reproduce an observation, one of two things is true. Either the observation is wrong, or the model is incomplete. Researchers have worked hard to explore the first possibility. Measurements of high redshift galaxy masses rely on interpreting the brightness and colour of light collected by Webb's instruments, and there are genuine sources of uncertainty in that process. Some scientists have argued that contamination from emission lines, bright spectral features produced by hot gas in star-forming regions, could make galaxies appear more massive than they truly are, inflating the estimated stellar mass by a factor of several. If that contamination is significant, some of the most extreme Webb galaxies might be less problematic for the standard model than they initially appeared. This is a real and legitimate scientific argument, and it is being taken seriously. But it does not resolve the full picture, because even accounting for these uncertainties, a significant number of the galaxies Webb has identified remain too massive, too luminous, and too structured for the standard timeline to easily explain. So researchers have begun, cautiously and with appropriate scientific humility, to explore the second possibility. That the model is incomplete, that something in the early universe was operating differently from what Lambda CDM assumes. Several candidate mechanisms have been proposed. One is that the efficiency of star formation in the early universe was dramatically higher than in the modern cosmos, that in those first dense, turbulent halos, a much larger fraction of available gas was converted into stars in a shorter period of time, producing the observed stellar masses without requiring new physics. Another proposal involves the behavior of dark matter itself, specifically whether it was truly cold in the early universe, or whether it had properties that allowed structure to form faster and more compactly than the standard model predicts. A third possibility, more radical and more debated, involves modifications to our understanding of how the early universe expanded, whether the growth of cosmic structure in the first few 100 million years proceeded at a different rate than our current equations suggest. None of these proposals has yet achieved consensus. The field is genuinely open, genuinely uncertain, and genuinely exciting in the way that only the frontiers of human knowledge can be. What Webb has done, in finding these impossible galaxies at the edge of time, is not destroy cosmology. It has not rendered everything we know worthless. What it has done is more precise and more valuable than that. It has identified a specific gap, a place where the map does not match the territory, and in doing so, it has given the next generation of theorists and observers a target, a specific, measurable, reproducible anomaly that any successful theory of the universe must eventually explain. That is how science actually progresses, not in smooth, triumphant accumulations of certainty, but in the uncomfortable recognition that something does not fit, and in the long, careful, occasionally brilliant work of figuring out why. There is something I find deeply moving about this process, even as I find it unsettling. The universe does not care about our models. It does not adjust its behavior to match our simulations. It simply is, in all its impossible complexity, and we must do the hard work of catching up. Webb has shown us that the cosmos was building extraordinary things at its very beginning, things faster and more impressive than we imagined, and the honest response to that, the scientifically and humanly honest response, is to look at the data, sit with the discomfort and say clearly, we do not yet fully understand this, and then get back to work. In the spring of 2024, a result emerged from the James Webb Space Telescope that quietly crossed a threshold scientists had been approaching for months with a mixture of excitement and disbelief. The object was designated JADES GS Z140. It is not a name that rolls easily off the tongue, and it will never appear on a poster in a child's bedroom. But among astronomers who study the early universe, it became, almost overnight, one of the most significant objects ever detected, because JADES GS Z140 is the most distant galaxy ever confirmed with spectroscopic precision. It exists at a redshift of 14.32, and that number, small as it looks on a page, places this galaxy at a distance and an age that redefines what we mean by the edge of observable time. Let me translate that redshift into something you can feel. A redshift of 14.32 means that the light Webb captured from this galaxy left its source approximately 290 million years after the Big Bang. The universe at that moment was not yet 300 million years old. It had not yet completed its first 300 million revolutions around a sun that did not yet exist. The Milky Way did not exist. Our solar system would not form for another 9 billion years. The atoms in your body, the oxygen in your lungs, the iron in your blood, none of the elements required to build biological life had yet been produced in any significant quantity. The universe was, by every measure, in its absolute infancy. And yet at that moment, in that impossibly young cosmos, JADES GS Z140 was already there, already shining, already massive, already, by any reasonable definition, a galaxy. To confirm this distance, astronomers did not simply measure the galaxy's colour and make an estimate. They used a technique called spectroscopy, the analysis of light broken into its component wavelengths, the way a prism splits white light into a rainbow. Every element absorbs and emits light at specific characteristic wavelengths, like a fingerprint. By spreading JADES GS Z140's light into its spectrum and identifying the fingerprints of known elements, in this case oxygen and other species, Astronomers could measure precisely how far those fingerprints had been shifted toward longer, redder wavelengths by the expansion of the universe. That shift gave them the redshift value. That redshift value gave them the distance, and the distance gave them the age. This was not an estimate, it was a measurement. Spectroscopic confirmation is the gold standard of observational cosmology, and JD's GS Z14-0 passed it. What makes this galaxy disturbing, genuinely productively disturbing, is not just its distance. It is what it contains at that distance. Astronomers estimate that JD's GS ZR14-0 already contained more than 500 million times the mass of our Sun in stars at the time its light was emitted. 500 million solar masses, in a universe less than 300 million years old. Think about what that requires. Stars do not form instantaneously. They condense from gas clouds over millions of years, then burn for millions or billions more. To accumulate 500 million solar masses in stars within the first 290 million years of the universe, star formation would have had to begin almost immediately after the first structures formed, and proceed at a rate that strains the limits of what our models allow. The universe was not slowly warming up. It was running at full speed almost from the moment it began. There is something else about JD's GS-Z14-0 that deserves its own moment of stillness. Astronomers detected the signatures of oxygen in its spectrum. Oxygen, in a galaxy less than 300 million years after the Big Bang. This matters enormously, because oxygen is not a primordial element. It was not created in the Big Bang. It is produced inside stars through the nuclear fusion of lighter elements, and then released into the surrounding gas when those stars die, either through stellar winds or, more dramatically, through supernova explosions. To have detectable oxygen in JD's GS-Z14-0, an entire generation of stars must have already been born, lived out their lives, and died before the galaxy's light left on its 13.5 billion-year journey to Webb's mirror. A full stellar life cycle, birth, burning, and death, completed within the first few 100 million years of cosmic history. It is almost too compressed to believe, and yet the oxygen is there, undeniable, written in the spectrum. The JADES program that produced this discovery, the name stands for GUST Advanced Deep Extragalactic Survey, is one of the most ambitious observational campaigns in Webb's first years of operation. It has invested hundreds of hours of telescope time staring at small patches of sky with extraordinary depth, building up light from the faintest and most distant sources the universe contains. JD's GS Z14-0 was not a lucky accident. It was found through systematic, patient, methodical observation, the kind that only becomes possible when you have an instrument as sensitive as Webb, and the willingness to use it at the absolute limits of its capability. The discovery represents not just a record, but a proof of concept. Webb can reach this far. Webb can find these objects, and it has barely begun. What lies beyond JD's GS Z14-0 is a question that is now actively on the table. Are there galaxies at even higher redshifts, at redshifts of 15, 16, 20, waiting to be found in the data Webb is still collecting? The theoretical lower limit is the epoch of reionization itself, the period when the first stars began ionizing the neutral hydrogen gas that filled the universe after recombination. Before that epoch, the universe was largely opaque even to infrared light, and no telescope can see through it. But within that window, between roughly 100 million and 500 million years after the Big Bang, there may be many more objects like JD's GS's Z14-0, objects that push our models further, that demand new explanations, that reveal the early universe to have been even more active and extraordinary than we currently understand. I find it worth pausing on what it means that we have a name for this object. JD's GS Z14-0. A string of letters and numbers assigned by human beings to a collection of ancient light that has been travelling toward us since before the Earth existed. We named it. We measured it. We decoded the chemistry of its stars from a distance of 13.5 billion light-years. There is something almost tender in that, the way we reach out across incomprehensible distance and time and say, quietly, we see you. We know you were there. You're not lost to the darkness, because we built an instrument sensitive enough to find you and patient enough to look. I want you to think about the photons that Webb captures from the most distant galaxies. Not abstractly, not as a concept, but as actual physical things, particles of light that were emitted by actual stars burning in actual galaxies nearly 14 billion years ago. These photons left their source when the universe was less than 300 million years old. They have been travelling ever since, through the expanding cosmos, through the great voids between galaxy filaments, past galaxy clusters whose gravity bent their paths ever so slightly, through billions of years of cosmic evolution, through the formation and death of countless stellar generations, past the formation of our own sun and solar system, across the remaining distance to a point 1 million miles from Earth, and into the golden mirror of a telescope that a small, young, improbable species built specifically to receive them. That journey is not a metaphor. Every photon Webb detects from these ancient galaxies actually made that trip, across all of that distance, across all of that time. But here is what makes those photons stranger still. They are not the same photons that left their source, or rather, they are the same photons in identity, the same particles, but they are profoundly changed. The universe through which they travelled has been expanding continuously since the moment of the Big Bang, and as it expanded, it stretched the fabric of space itself, and light travelling through that stretching space gets stretched along with it. The wavelength of each photon grows longer as the cosmos expands. A photon that began its journey as visible light, the kind your eyes can detect, has been stretched over 13.5 billion years of cosmic expansion into something your eyes cannot see at all. It arrives at Webb as infrared radiation, as heat light, as a whisper so long and slow and drawn out that it exists at the very edge of detectability. This is why Webb was built to see in infrared. Every telescope before it that tried to observe the earliest galaxies was working in visible light, the light our eyes and most instruments naturally detect. But the oldest light in the universe does not arrive as visible light anymore. It arrives redshifted far beyond what our eyes can process, stretched into infrared wavelengths by the same expansion of space that carries those ancient galaxies away from us. Hubble, for all its magnificence, was largely blind to this light. It could push toward the infrared at its limits, but not nearly far enough. Webb was designed from the ground up to live in the infrared, to be sensitive precisely to the wavelengths, where the oldest, most distant, most scientifically precious light in the universe actually arrives. That design choice, made decades before launch, is why Webb can see what no instrument before it could. The concept of infrared light is worth spending a moment with, because it is easy to think of it as somehow lesser than visible light, a dim or faint version of the real thing. It is not. Infrared is simply light at wavelengths, slightly longer than what our eyes evolved to detect. Everything warm emits infrared radiation. Your body emits it right now, as does every surface in the room around you. The sun emits vast quantities of it, alongside the visible light that warms the earth. Infrared cameras can see in total darkness by detecting the heat signatures of objects too cool to glow in visible wavelengths. It is abundant, energetic, and entirely real, just invisible to the particular biological sensors evolution gave us. Webb's instruments are tuned to wavelengths between roughly 0.6 and 28 micrometers, a range that spans the near-infrared and mid-infrared, covering the redshifted light of galaxies from the earliest cosmic epochs and also revealing the chemical signatures of distant atmospheres, stellar nurseries, and planetary systems in ways no previous telescope could match. To detect infrared light without being blinded by its own thermal glow, Webb's instruments must be kept at temperatures that are almost incomprehensible in their coldness. The main camera and spectrographs operate at around minus 233 degrees Celsius. The mid-infrared instrument goes even further, cooled by an active cryocooler to minus 266 degrees Celsius, just 7 degrees above absolute zero, the coldest temperature that physics permits. At these temperatures, the thermal vibration of atoms in Webb's own structure is reduced to almost nothing, and the instrument's self-generated infrared noise drops below the threshold where it would contaminate the observations. The telescope becomes, in effect, nearly invisible to itself, a cold, silent eye, sensitive to the faintest possible whispers of ancient light, designed to mistake nothing for something and to miss nothing that is actually there. When those ancient photons finally reach Webb's primary mirror after their 13.5 billion year journey, they strike the gold-coated beryllium surface and are reflected toward a secondary mirror, then directed into one of 4 scientific instruments. Each instrument breaks the incoming light into its component wavelengths, measuring the brightness at each one with extraordinary precision. From those measurements, astronomers can reconstruct the spectrum of the source, its chemical composition, its temperature, its velocity, its distance. A single spectrum from a distant galaxy contains, encoded in the pattern of bright and dark lines at specific wavelengths, a remarkable amount of information. The presence of oxygen, the rate of star formation, the existence of a supermassive black hole at the galaxy's centre, all of it written in light that left its source before the Earth existed, decoded by instruments built on a world those ancient photons could not have known was coming. There is a quality to this that I find almost unbearably moving on quiet nights. Light is patient in a way nothing else in physics is. It travels at the maximum speed the universe permits. Nothing with mass can ever reach it. And yet it takes time, enormous, almost geological stretches of time, to cross the distances between galaxies. Those photons from JD's GS Z14 to 0 began their journey when the universe was less than 300 million years old, and arrived at Webb's mirror when the universe was 13.8 billion years old. They travelled for 13.5 billion years. They crossed a distance that, in that time, the expansion of the universe has stretched to approximately 33 billion light years, and they arrived. They made it. After all of that, after all of those billions of years of silent travel through the expanding dark, they struck a golden mirror built by creatures who barely existed on cosmic timescales. And they told us something true about the beginning of everything. That, to me, is one of the most astonishing facts in all of science. Not just that the universe is vast, but that its oldest light is still arriving, still carrying information, still willing to be read, if only we build the instruments sensitive enough to receive it. Before there were galaxies, there were stars, and before there were the kinds of stars we know today, stars like our Sun, rich in carbon and oxygen and iron and all the elements that make complex chemistry possible. There was a different kind of star entirely, a kind that no longer exists anywhere in the observable universe, a kind so extreme, so alien to our modern cosmic experience that astronomers have never directly observed one. We know they must have existed. The physics demands it. The chemical record of the universe requires it. And Webb, in its deepest observations of the earliest cosmos, may be finding their fingerprints at last, traces of a stellar generation so ancient it predates everything we have ever seen, burned into the spectra of the youngest galaxies we have ever detected. These stars are called Population 3 stars, and their story begins with a simple and profound fact about the Big Bang. The Big Bang did not produce a rich mixture of elements. It produced almost exclusively hydrogen and helium, with the tiniest trace of lithium, 3 elements, simple and light. The raw material of an infant universe that had not yet learned how to build anything more complex. The periodic table as we know it, with its dozens of elements from carbon to iron to gold to uranium, did not yet exist. It had to be built, atom by atom, inside the cores of stars, through the process of nuclear fusion, where lighter nuclei are forced together under conditions of extreme heat and pressure to form heavier ones. Every element heavier than helium in the universe was forged inside a star, including every atom in your body. But the first stars had none of that inheritance. They began with only hydrogen and helium, and they had to make everything else themselves. With only hydrogen and helium available, and with no heavier elements to help gas clouds radiate away their heat and collapse more efficiently, the first stars are thought to have formed very differently from modern stars. In the present-day universe, clouds of gas collapse into stars across a wide range of masses, from small dim red dwarfs a fraction of the sun's size to massive blue giants tens of times larger. The presence of heavier elements in modern gas clouds allows them to cool more rapidly through radiation, fragmenting into smaller pieces and producing a distribution of stellar sizes. But in the early universe, without those cooling agents, gas clouds could not fragment as efficiently. They collapsed into larger, hotter, more concentrated objects. Theoretical models suggest that population 3 stars may have ranged from roughly 10 to perhaps 1,000 times the mass of our Sun. Some estimates push even higher. They were, in the language of astrophysics, massive to an almost monstrous degree. A star 1,000 times more massive than our Sun is difficult to comprehend. Our Sun, which contains more than 99% of all the mass in the solar system, which could fit 1.3 million Earths inside it, which has been burning steadily for 4.6 billion years and will continue for roughly another 5 billion. A star 1,000 times more massive than that is a thing of almost violent extravagance. Its core temperature would be many times higher than our Sun's. The rate at which it fuses hydrogen into helium, and then helium into carbon, carbon into oxygen, oxygen into neon, and so on up the chain of elements, would be correspondingly ferocious. Where our Sun will live for roughly 10 billion years, a population 3 star of extreme mass might have a lifespan measured in just a few million years. It would burn through its fuel at a rate so extraordinary that it would exhaust an entire stellar lifetime in the cosmic equivalent of an eye blink. And then it would die, violently, catastrophically. In explosions so energetic they are called hypernovae or pair instability supernovae, events that for a brief period could outshine entire galaxies. In these deaths, the population 3 stars scattered the heavy elements they had forged in their cores, carbon, oxygen, nitrogen, silicon, iron, out into the surrounding gas, seeding it for the first time with the chemical complexity that would eventually make planets possible, and life. These ancient, invisible, never directly observed stars are, in the most literal sense, the ancestors of everything. Every carbon atom in every living thing on Earth was forged in a star. The iron in your hemoglobin was produced in a stellar core and scattered by a stellar explosion. We are not metaphorically made of stars, we are materially made of them, and the chain of stellar deaths that produce the atoms in your body may trace all the way back to population 3 stars burning in galaxies like JADES GS ZF14-0 in the first few 100 million years after the Big Bang. What Webb has potentially found in that galaxy and in others from the same epoch is the chemical signature of this first generation. The detection of oxygen in JADES GS Z14-0 in a galaxy less than 300 million years after the Big Bang means that at least one generation of stars had already lived and died before that galaxy's light left on its journey to us. Those stars created the oxygen, scattered it, and it was already present in detectable quantities in the interstellar gas of this ancient galaxy. Webb did not see the population 3 stars directly. They're too short-lived and too early to be captured in the act. But their afterlife is visible. Their chemical legacy is written into the spectrum of the galaxy that came after them. Webb is reading a message left by stars that no longer exist, in a language made of light, across a distance of 13.5 billion light-years. There is something deeply affecting about this if you let it settle. The universe has been building and rebuilding itself for nearly 14 billion years. Each generation of stars takes the material left by the previous one and uses it to make something more complex, more varied, more chemically rich. The first stars made carbon and oxygen and iron from almost nothing. Later stars incorporated those elements and made even heavier ones. Eventually, in the right conditions, around the right star in the right part of the right galaxy, that accumulated complexity produced planets, oceans, cells, minds that could look up at the night sky and wonder where they came from. You are the product of that chain, a chain that began in the furnaces of population 3 stars burning in ancient galaxies at the edge of time. The fact that Webb is now finding traces of those first fires, reading their chemical legacy in the oldest light we have ever captured, feels like something more than science. It feels like the universe tracing its own family tree, and finding, at the very root of it, a kind of fire so old and so enormous that it has no name except the one we gave it, the first light in the dark. If you could somehow remove yourself from the Earth and float freely in the universe, not near any star, not near any galaxy, just out in the open cosmos, the first thing that would strike you is not the beauty of the stars, it is the emptiness, the vast, overwhelming, almost aggressive emptiness of space. Because here is something that the images we see of the universe, those gorgeous photographs of galaxies and nebulae and star clusters, systematically conceal from us. They are images of the exceptions. They show us the places where matter is gathered, where light is produced, where structure exists. They do not show us what fills the overwhelming majority of the universe's volume, and what fills it, with almost incomprehensible thoroughness, is nothing at all. The universe, on its largest scales, is structured like a cosmic web. Filaments of dark matter and ordinary matter stretch across hundreds of millions of light-years, connecting galaxy clusters at their intersections like the nodes of an enormous net. Along these filaments, galaxies cluster and flow, pulled by gravity into loose associations and dense clusters that represent the most spectacular concentrations of matter in the observable cosmos. But between the filaments, in the vast regions enclosed by the Webb, there is almost nothing. These regions are called cosmic voids, and they are among the largest discrete structures in the known universe. Some voids span hundreds of millions of light-years from edge to edge. The Bootes void, one of the most well-known, stretches roughly 330 million light-years across. Inside it, there are almost no galaxies, almost no stars, almost no atoms of ordinary matter in any detectable concentration. Just space, cold, dark, expanding space, with a handful of galaxies scattered through it so thinly they barely register. Think about what 330 million light-years of emptiness means in practice. If you were to travel at the speed of light, the fastest speed the universe permits, it would take you 330 million years to cross the Bootes void from one side to the other. In that time, on a planet like Earth, complex multicellular life could have evolved and been extinguished multiple times. Entire geological eras could have passed. Stars could have formed, lived out their entire lifespans and collapsed into stellar remnants, and you would still be crossing an empty room, a room with nothing in it worth stopping for. No planets, no stars, no galaxies, just the slow, silent expansion of space itself, carrying the void's boundaries outward into an even larger emptiness beyond. The fraction of the universe's volume occupied by matter is almost too small to express meaningfully. If you were to compress all the matter in the observable universe, all the stars, all the gas, all the dust, all the dark matter, and distribute it uniformly across the full volume of the observable cosmos, the average density would be roughly equivalent to a few hydrogen atoms per cubic meter. A cubic meter, roughly the volume of a large microwave oven, containing perhaps 5 or 6 atoms. That is the average density of the universe. Most of space is not a near vacuum. It is closer to a perfect vacuum than anything we can produce in a laboratory on Earth. The molecules of air in the room around you right now represent an almost absurdly extravagant concentration of matter by cosmic standards. You are, in the most literal sense, a bizarre and extreme exception to the universe's general preference for emptiness. Webb, in its deep observations of the early universe, has been mapping the large-scale structure of the cosmos across time, tracing how the cosmic web formed and evolved, how voids grew as matter drained away from them into the surrounding filaments, how the distribution of galaxies shifted and clustered over billions of years. What these observations reveal is that the voids we see today were already beginning to form in the very early universe. Even in the epoch of the first galaxies, the seeds of the cosmic web were present, slight variations in the density of matter that would, over billions of years of gravitational amplification, grow into the vast filaments and enormous voids of the modern cosmos. The emptiness we see today is not an accident. It is the direct descendant of quantum fluctuations in the infant universe, written across the largest scales of existence. There is something that I find genuinely difficult to hold in my mind about cosmic voids, and I want to try to share it with you. These voids are not static. They're growing. The expansion of the universe is accelerating, driven by the mysterious force we call dark energy, and as it accelerates, the voids expand faster than the filaments can replenish them. Matter drains away from the interior of voids toward the surrounding structures, leaving the voids emptier and larger with each passing billion years. In the far future, tens of billions of years from now, the voids will dominate the universe's volume even more completely than they do today. Galaxies will be separated by distances so vast that, from inside any one galaxy, the rest of the universe will have receded beyond the observable horizon. Each island of matter will be alone in an otherwise empty cosmos, unable to see or interact with any other. The silence between the galaxies, already profound, will become absolute. I think about this on clear nights, when the sky's dark enough to see the faint smudge of the Milky Way overhead. The stars look close together up there, a dense river of light spanning the sky. But that density is an illusion of proximity. The nearest star to our Sun is more than 4 light-years away. The space between stars in our galaxy is, by any human measure, almost entirely empty. And our galaxy itself, vast as it is, containing hundreds of billions of stars, is separated from its nearest large neighbour by 2.5 million light-years of void. We live, all of us, in a small warm island of light and matter, surrounded on all sides by an ocean of darkness so immense it has no shores we will ever reach. Webb is teaching us to see that darkness more clearly, not to fear it, but to understand it as part of the structure, as the necessary context in which matter and light and life can exist. The voids are not failures of the universe, they are its architecture. They define the shape of the cosmic web the way silence defines the shape of music. Without the emptiness between the notes, there is no melody. Without the vast dark voids between the galaxy filaments, there is no structure to the cosmos at all. Just a uniform fog, dense and featureless, in which nothing as complex as a galaxy, or a star, or a planet, or a mind capable of wondering about all of this could ever have formed. The silence between the galaxies is not empty of meaning. It is, in its own quiet way, the reason we exist at all. Here is a fact about the universe that I want you to sit with for a moment, because it is one of the strangest and most humbling things science has ever discovered. Everything you have ever seen, touched or measured, every star, every planet, every ocean, every mountain, every atom in every living thing that has ever existed on Earth, all of it, the entire physical world as you experience it, accounts for approximately 5% of the total energy content of the universe. 5%. The remaining 95% is made of things we cannot see, cannot touch, cannot directly detect with any instrument ever built, and do not yet fully understand. We have given these things names, dark matter and dark energy, but naming something is not the same as understanding it. And the honest truth, the one that cosmologists carry quietly with them through their careers, is that the majority of reality is currently invisible to us, possibly forever. Dark matter was not invented to fill a gap in a theory. It was discovered by observing a discrepancy between what we could see and what the universe was actually doing. The first strong evidence came from galaxies themselves. In the 1930s, the Swiss astronomer Fritz Zwicky noticed that the galaxies in the Coma cluster were moving too fast. If the only mass present were the visible stars and gas, the gravitational force holding the cluster together would be far too weak to prevent the galaxies from flying apart at the speeds he measured. Something else had to be there, something massive, something invisible, providing the extra gravitational pull needed to keep the cluster bound. Zwicky called it dunkel materie, dark matter. For decades the idea was treated with skepticism. Then, in the 1970s, the astronomer Vera Rubin measured the rotation of individual galaxies and found the same problem at smaller scales. Stars at the outer edges of galaxies were orbiting too fast for the visible mass to explain. The dark matter was not just in clusters, it was everywhere, surrounding every galaxy, permeating every structure in the cosmos. What dark matter actually is remains one of the deepest open questions in all of physics. It does not emit light. It does not absorb light. It does not interact with ordinary matter through the electromagnetic force in any detectable way. It interacts only through gravity, and possibly through the weak nuclear force, which is why one leading candidate for its identity is a class of hypothetical particles called weakly interacting massive particles, or WIMPs. Other candidates include axions, sterile neutrinos, primordial black holes, and a range of other exotic possibilities that theoretical physicists have been debating for decades. None of these candidates has been definitively confirmed by experiment. Dark matter remains, after nearly a century of investigation, an entity known only by its gravitational effects, like a vast invisible hand shaping the cosmos without ever showing itself. Dark matter makes up roughly 27% of the universe's total energy content. It is the scaffolding on which the cosmic web is built. Without it, gas would not have clumped quickly enough to form the first stars and galaxies. The filaments and nodes of the large-scale structure would not exist. The universe would be a far smoother, far emptier, far less interesting place, one in which complex structures like galaxies, and therefore planets, and therefore life, might never have emerged at all. In this sense, dark matter is not an exotic curiosity at the margins of cosmology. It is a foundational ingredient of everything that exists, including you. You're here in part because of a substance whose nature we do not understand, whose particles we have never directly detected, and whose properties we can only infer from the way galaxies move and the way the cosmos is shaped. And then there is dark energy, which is stranger still. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that won them the Nobel Prize and upended cosmology. The universe is not just expanding, it is expanding faster and faster with time. Something is pushing space apart, overcoming the gravitational attraction of matter on the larger scales and driving the cosmic expansion to accelerate. That something is dark energy. It accounts for roughly 68% of the universe's total energy content, by far the dominant component of the cosmos, and we have almost no idea what it is. The leading mathematical description, a term in Einstein's equations called the cosmological constant, fits the data well but offers no physical explanation for why it has the value it does. The discrepancy between the theoretically predicted value of the cosmological constant and the observed one is, depending on how you calculate it, somewhere between 50 and 120 orders of magnitude. That is arguably the largest discrepancy between theory and observation in the history of science. Webb is contributing to this investigation in ways that were not fully anticipated, even when it was designed. By observing the most distant galaxies across cosmic time, Webb is helping astronomers trace the history of the universe's expansion with unprecedented precision, measuring how the rate of acceleration has changed over billions of years, and testing whether dark energy is truly constant or whether it varies with time. The answer matters enormously. A dark energy that changes over time would require entirely new physics beyond Einstein's general relativity. Early hints from Webb's data, combined with results from other surveys, have suggested that the behavior of dark energy may be more complex than the simplest cosmological constant model predicts. The field is watching carefully, and the results are not yet definitive. But the direction of the evidence is pointing towards something more interesting and more challenging than the current standard model allows. What I find most striking about dark matter and dark energy, the thing that stays with me on quiet nights, is not the mystery of what they are. It is what their existence says about the limits of our perception. We evolve senses capable of detecting visible light, sound, touch, taste, and smell. Those senses are magnificently well tuned for navigating a world of moderate scales, for finding food, avoiding predators, building relationships, surviving on the surface of a small planet. But they were not built to perceive the universe at its true scales. 95% of reality is invisible to our unaided senses and undetectable by most of our instruments. We live inside a cosmos whose fundamental nature we're only beginning, with great effort and ingenuity, to glimpse. Webb sees further than any instrument before it. But it still sees in only 5% of the universe. The rest, the dark scaffolding, the accelerating void, the invisible architecture on which everything is built, remains beyond its reach. Beyond all of our reach, for now. There is a question that sits at the edge of everything Webb is doing, a question that the telescope cannot answer directly, but that its discoveries keep pushing us toward with increasing urgency. It is perhaps the oldest question in human thought, dressed now in the language of modern physics. What came before the beginning? What existed, if anything, before the Big Bang? Before space? Before time? Before the first particle, the first photon, the first quantum of energy? Before the universe itself? It is the kind of question that, if you hold it long enough in the quiet of a late night, produces a particular variety of vertigo. Not the dizziness of heights, but the dizziness of standing at the edge of what the human mind can even attempt to conceive. And the honest answer, the only scientifically defensible answer we currently have, is that we do not know. We may never know. The question may not even be meaningful in the way we are asking it. Here is why. Our understanding of time itself is inseparable from our understanding of the universe. According to general relativity, Einstein's theory of gravity, which describes the large-scale structure and behavior of the cosmos with extraordinary precision, time is not a fixed background against which events occur. It is a dimension woven together with the 3 dimensions of space into a single 4-dimensional fabric called space-time. And space-time, in general relativity, is not eternal and independent. It is created by and inseparable from the matter and energy it contains. At the moment of the Big Bang, according to our current best understanding, space-time itself came into existence. There was no time before the Big Bang because time began at the Big Bang. Asking what happened before the Big Bang is, in this framework, like asking what is north of the North Pole. The question contains a hidden assumption that there was a before which the physics does not support, and yet physicists do not simply accept this answer and move on, because general relativity, for all its success, breaks down at the extreme conditions of the Big Bang itself. At the moment of infinite density and infinite temperature that our equations describe as the universe's origin, a moment called the initial singularity, the equations of general relativity produce results that are not physically meaningful. Infinities appear. The theory destroys itself. This tells us not that a singularity actually existed, but that general relativity is incomplete, that it requires a successor theory, a quantum theory of gravity, to describe what actually happened at the universe's first moment. And that theory, despite decades of work by some of the most brilliant minds in physics, does not yet exist in its complete form. We are trying to understand the beginning of time with tools that are not yet adequate to the task. In the absence of a complete theory, physicists have proposed a range of scenarios for what might have preceded or produced the Big Bang. One of the most influential is cosmic inflation, the idea that the very early universe underwent a period of extraordinarily rapid expansion, doubling in size again and again in a tiny fraction of a second, smoothing out the initial conditions and seeding the universe with the quantum fluctuations that would eventually grow into the large-scale structure we observe today. Inflation is supported by observational evidence. The patterns in the cosmic microwave background match its predictions remarkably well, but the mechanism that drove it and what happened before it began remain unclear. Many versions of inflation predict that it is eternal, that it continues forever in regions beyond our observable universe, occasionally producing bubble universes like our own in a process called eternal inflation. In this picture, our universe is one bubble in an infinite, ever-inflating multiverse, a single note in an endless cosmic symphony that plays forever in the dark. Another class of proposals involves cyclic cosmologies, models in which the universe does not have a singular beginning, but instead oscillates or bounces through successive cycles of expansion and contraction. In some versions, our Big Bang was not the first event in the universe's history, but the latest in a series of cycles, each ending in a contraction and rebounding into a new expansion. The mathematical details of these models are complex and contested, and the question of whether they are genuinely distinct from a universe with a single beginning or merely a reframing of the same situation is one physicists actively debate. But the core idea that the Big Bang was a transition rather than an absolute beginning offers at least a conceptual escape from the hard wall of the initial singularity. Perhaps the most radical and philosophically vertiginous proposal is the one associated with the physicist Alexander Vilenkin and others, which suggests that the universe emerged from literally nothing through a quantum tunneling event. In quantum mechanics, particles can appear spontaneously from a vacuum, borrowing energy from the vacuum fluctuations that quantum mechanics says are always present even in empty space. Extrapolated to the extreme, this idea suggests that the universe itself, the entirety of space-time, matter and energy, may have spontaneously nucleated from a quantum vacuum state in which there was no space, no time, and no energy at all in the classical sense. Something from nothing, not as a miracle, but as a quantum probability. The universe, in this view, is not the result of a cause in the ordinary sense. It is a fluctuation, an accident, the most consequential accident in the history of existence. Webb cannot see before the Big Bang. No instrument can. The cosmic microwave background, the oldest light we can detect, forms a wall at 380,000 years after the beginning. Beyond it, the universe was opaque and no photons escaped to tell us what came before. But what Webb is doing, by probing the earlier structures that formed after the Big Bang, is giving us increasingly precise constraints on the initial conditions of the universe, the exact temperature fluctuations, the exact distribution of matter and energy at the earliest moment we can observe. And those constraints, fed into theoretical models, help physicists narrow down which proposals for the universe's origin are compatible with what we actually see. It is indirect, patient, careful work. The kind of work that does not produce dramatic headlines, but that, over decades, quietly closes in on the deepest questions ever asked. I want to leave you with something about this question that I find more comforting than terrifying, even though the vertigo is real. The fact that we are asking it at all, the fact that the universe has produced creatures capable of looking back at their own beginning and wondering what preceded it, is itself one of the most extraordinary facts about existence. We are matter that has organized itself into a form capable of questioning its own origin. Whatever came before the Big Bang, whatever produced the conditions that allowed 13.8 billion years of cosmic evolution to unfold into stars and galaxies and planets and minds, it produced us, and we're asking the question that, on its own, feels like something worth sitting quietly with, in the dark, before sleep. Webb has shown us galaxies that existed less than 300 million years after the Big Bang. It has revealed that the early universe was building massive, complex structures far faster than we expected. It has found oxygen in ancient light, traced the chemical legacy of the first stars, and pushed the boundaries of what we can observe all the way to the edge of the observable cosmos. And in all of that extraordinary depth of observation, across all of that staggering volume of space and time, it has found no signal of intelligence, no transmission, no megastructure, no artifact, no indication, anywhere in the ancient or modern universe that any mind other than our own has ever looked up at the stars and wondered. That silence is not a minor footnote to Webb's discoveries. It is, in its own quiet way, one of the most profound and disturbing things the telescope has confirmed. The question of whether we are alone in the universe is not new. But Webb has given it a new and sharper edge. Consider the numbers that are now better established than ever. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Many of those stars host planetary systems. The fraction of those planets that might exist in the habitable zones of their stars, not too hot, not too cold, with liquid water potentially present, is estimated to be in the hundreds of billions across the observable cosmos. And those are just the planets we can infer statistically. The actual number of worlds with some form of liquid chemistry is almost certainly larger. The universe is not stingy with the ingredients for life. It makes planets the way it makes stars, abundantly, continuously, across billions of years and trillions of locations, and yet, silence. This is the Fermi paradox, named after the physicist Enrico Fermi, who reportedly posed the question during a casual lunch conversation in 1950. If the universe is so vast, so old, so filled with potentially habitable worlds, where is everybody? The question has sharpened considerably in the decades since. The Milky Way alone is roughly 13 billion years old. The first stars formed even earlier. If life arose anywhere in our galaxy, even 1 billion years before it arose on Earth, a conservative assumption in a galaxy 13 billion years old, that civilization would have had 1 billion years to develop, to spread, to build things detectable from across interstellar distances. 1 billion years is enough time, at even modest rates of expansion, to colonize the entire galaxy. And yet we see nothing. No signals. No megastructures blocking starlight. No patterns in cosmic radiation that suggest engineering on astronomical scales. Nothing. Webb deepens the paradox in a specific way. The galaxies it has found in the early universe existed 13 billion years ago. Some of those ancient galaxies may have contained stars with planets that developed life billions of years before our sun was even born. If any of those ancient civilizations survived long enough, grew powerful enough, and spread far enough, the effects of their existence should, in principle, be detectable across cosmic scales. The universe has had enough time, more than enough time, for intelligence to have made its mark on the observable cosmos. Webb, with its extraordinary sensitivity and its view across the full breadth of cosmic history, has looked for that mark. It has not found it. Everywhere we look, in the oldest light and the newest, the universe appears pristine, unmodified, unmarked by the hand of any intelligence other than our own. There are many proposed resolutions to the Fermi paradox, and they range from sobering to terrifying. The most optimistic is simply that life is rare, that despite the abundance of potentially habitable planets, the specific chain of chemical events required to produce self-replicating molecules, and then cells, and then complex multicellular life, and then intelligence, is so improbable that it has happened only once, or very rarely, in the observable universe. In this view, we are not typical. We are an accident of almost inconceivable specificity, and the silence around us is simply the sound of a universe that has not yet managed, anywhere else we can see, to produce something like us. This is sometimes called the rare Earth hypothesis, and Webb's data, by showing no signs of intelligent modification of the cosmos, is at least consistent with it. A darker resolution is what some researchers call the Great Filter, the idea that there exists some barrier, some step in the development of intelligent life, that almost nothing survives. The filter might lie behind us, perhaps the emergence of complex cells from simple bacteria, which took nearly 2 billion years on Earth, and may be extraordinarily improbable elsewhere. Or the filter might lie ahead of us, a barrier that all sufficiently advanced civilizations eventually encounter and fail to pass. A self-inflicted extinction, perhaps, or a physical limit on how far any civilization can grow before it collapses. If the Great Filter lies ahead, then the silence around us is not reassuring. It is a warning. It is the universe telling us, through the absence of anyone else's voice, that the road we are on is one that others have walked and not returned from. Webb has also expanded our understanding of the variety of potentially habitable environments in the universe. Its spectroscopic capabilities allow it to analyze the atmospheres of exoplanets, planets orbiting other stars, by measuring how starlight filters through their atmospheric gases during a transit. It has already detected water vapor, carbon dioxide and sulfur dioxide in the atmospheres of planets outside our solar system. It is looking for the chemical signatures that, on Earth, are associated with biological processes, oxygen, methane, ozone, in combinations that would be difficult to explain without life. It has not found conclusive biosignatures yet, but it is looking, and the search is real and serious and ongoing. What I keep returning to in the quiet space between the data and the questions is the particular quality of the silence. It is not a hostile silence. It is not a silence that says the universe is empty of wonder. Everything Webb has shown us, the ancient galaxies, the first stars, the chemical richness of the cosmos, says the opposite. The universe is extravagantly generous with matter and energy and time. It has been building and burning and evolving for nearly 14 billion years, and in all of that time, in all of that space, we have found, so far, only ourselves, looking up, wondering, building golden mirrors and sending them 1,000,000 miles into the dark to ask the oldest question there is. Are we alone? The universe has not yet answered, and in the meantime, we keep looking. Because the act of looking, the refusal to accept the silence as final, the insistence that the question matters, may be the most distinctly and beautifully human thing we do. There is a boundary around us that no telescope will ever pierce, not Webb, not any instrument that could conceivably be built in the future, no matter how sensitive, no matter how large, no matter how perfectly engineered. It is not a wall of matter or a barrier of energy. It is a horizon, a limit imposed not by our technology, but by the speed of light and the age of the universe. Beyond it, space continues. Almost certainly it continues for an enormous distance, perhaps infinitely. But the light from what lies beyond has not had time to reach us yet, and in an accelerating universe, much of it never will. We live inside a bubble of knowable space, surrounded on all sides by a cosmos we can never directly observe, never measure, never confirm. The edge of the observable universe is the most absolute frontier in all of science, and what lies beyond it is, by definition, beyond us. The observable universe extends roughly 46 billion light-years in every direction from Earth. That number surprises many people when they first encounter it, because the universe is only 13.8 billion years old. So how can we see 46 billion light-years away? The answer lies in the expansion of space itself. The light we are receiving now from the most distant objects left its source long ago, when those objects were much closer to us. In the time that light has been travelling, the universe has been expanding, carrying those objects much farther away than they were when the light departed. The galaxy that emitted the light we are receiving right now from the edge of our observable horizon was, at the moment of emission, only a few billion light-years away. Today that same galaxy is roughly 46 billion light-years distant, and moving away from us faster than the speed of light, carried by the expansion of space itself, in a way that does not violate the cosmic speed limit because it is space that is moving, not the galaxy moving through space. This distinction matters because it means that the most distant galaxies we can currently see are already, right now, unreachable. Not just difficult to reach, permanently, irreversibly beyond any possible contact. If we sent a signal toward one of the galaxies at the edge of our observable horizon at the speed of light, the expansion of the universe would carry that galaxy away faster than our signal could close the gap. Our signal would never arrive. The universe is not just large. In the relevant sense, the sense that matters for any possible communication or contact, it is already effectively infinite. The horizon is not just a limit of our current instruments. It is a limit built into the structure of reality as it currently exists, driven by the accelerating expansion that dark energy is producing right now, in this moment as you listen. And the horizon is shrinking, not in the sense that the observable universe is getting smaller. It is actually growing because light from slightly more distant regions continues to arrive as time passes. But the number of galaxies that will ever be observable to us is decreasing. In the far future, the accelerating expansion will carry more and more galaxies beyond our horizon permanently. They will redshift to invisibility, their light stretched to infinite wavelengths, their signals diluted beyond any possible detection. Astronomers calculate that in roughly 150 billion years, the only galaxies visible from the Milky Way will be those gravitationally bound to our local group, the small cluster of galaxies that includes Andromeda and a few dozen smaller companions. Everything else, the 2 trillion galaxies Webb can currently detect, will have vanished beyond the horizon, gone as completely as if they had never existed. A civilization living at that future epoch would look out at the night sky and see almost nothing. They would have no evidence that the rest of the universe exists at all. They might conclude, entirely rationally based on everything they could observe, that they were alone in an almost empty cosmos. And they would be wrong, in the same way that we might be wrong about things our horizon prevents us from seeing today. This is one of the most disturbing implications of the accelerating universe, and Webb is helping us understand it with increasing precision. We happen to live at a cosmologically privileged moment, a time when the universe is old enough to have produced galaxies, stars, planets, and intelligent life, but young enough that the cosmic horizon still encompasses an enormous, rich, observable cosmos. We can see the ancient galaxies. We can measure the cosmic microwave background. We can reconstruct the history of the universe from its first moments to the present. Future astronomers, if any exist, will not be so fortunate. The window of cosmic observability is open now. Webb is looking through it with the best instruments we have ever built. And what we are learning in this window about the early universe, about galaxy formation, about the large-scale structure of the cosmos, may represent knowledge that can never be recovered once the universe has expanded beyond our reach. Beyond the observable horizon, physics says that space almost certainly continues. How far is genuinely unknown. Some cosmological models, particularly those based on eternal inflation, suggest that the universe extends infinitely in all directions, filled with a vast and varied landscape of regions, each potentially with different physical constants, different particle masses, different laws governing the behavior of matter and energy. In some of these regions, conditions for life might exist. In others, the laws of physics might be so different that atoms cannot form, stars cannot burn, and complexity of any kind is impossible. We cannot observe any of this. We can only infer it from the mathematics of the theories that best describe what we can observe. The multiverse, if it exists, is not a scientific hypothesis in the traditional sense, because it makes no predictions we can currently test. It is the shadow that our best theories cast beyond the edge of what is knowable. I want to stay with the horizon for a moment longer, because I think it deserves more than a passing acknowledgement. There is something genuinely, existentially significant about living in a universe with a built-in limit on what can ever be known. It is not a temporary limit, waiting to be overcome by better technology. It is a permanent feature of reality, the universe's own privacy, maintained by the laws of physics. Most of what exists is hidden from us not by ignorance, but by geometry and time. The cosmos is not withholding its secrets out of hostility. It is simply larger than what any finite observer, in any finite time, can fully see. Webb pushes our view as far as physics allows, to within a few 100 million years of the beginning, to within a few billion light-years of the horizon. It sees farther than anything before it, and still the boundary remains. The edge of the observable universe is the place where human curiosity runs up against the hardest possible wall. Not a wall of stone or energy, but a wall of time and distance, absolute and serene, beyond which the cosmos keeps its own counsel, in a silence no instrument will ever break. At some point in this journey, somewhere between the ancient galaxies and the cosmic voids, somewhere between the first stars and the edge of the observable universe, the story stops being only about the cosmos and starts being about us. About what it means to be the kind of creature that asks these questions. About what it means to live on a small, warm, improbable planet orbiting an ordinary star in one of 2 trillion galaxies, and to have developed, against all statistical expectation, the capacity to wonder about all of it. Webb is the most powerful telescope ever built, but what it is ultimately teaching us is not just about the universe out there. It is about the universe in here, the one that lives inside the minds of the beings who built it, pointed it at the dark, and waited to see what the dark contained. Let me start with something concrete and physical, because it grounds everything else. The iron in your blood, the iron in every red blood cell carrying oxygen through your body right now as you listen, was not produced on Earth. It was not produced in our solar system. It was forged in the core of a massive star that lived and died long before our sun was born. In the final moments of that star's life, as it exhausted its fuel and collapsed under its own gravity, the conditions in its collapsing core produced iron in quantities that could not have been created any other way. The star exploded. The iron scattered into the surrounding interstellar medium. Eventually, over millions of years, that enriched gas became part of a cloud that collapsed into our solar system, into the sun, into the Earth, and ultimately into you. The iron in your hemoglobin is recycled stellar material. You carry the remnants of dead stars in your blood. The carbon in your DNA has a similarly ancient pedigree. Carbon is produced in the cores of stars through a process called the triple alpha reaction, in which 3 helium nuclei fuse to form a single carbon nucleus under conditions of extraordinary temperature and pressure. Every carbon atom in the organic molecules that make up your cells was built in a stellar furnace, expelled into space when the star died, mixed into the interstellar medium, incorporated into a molecular cloud, collapsed into our solar nebula, and eventually assembled by the blind chemistry of a young planet into the first self-replicating molecules that would, billions of years later, become you. The oxygen you're breathing right now was fused in stellar cores, the nitrogen in your proteins, the phosphorus in your bones, the calcium in your teeth, all of it stellar, all of it ancient, all of it recycled from fires that burned before the Earth existed. Webb is tracing this chain backward with a clarity and depth we have never had before. The oxygen it detected in JADI's GS Z140, that ancient galaxy burning less than 300 million years after the Big Bang, represents some of the earliest heavy elements ever produced in the universe. The stellar generations that made that oxygen were among the first to enrich the cosmos with anything beyond hydrogen and helium. That enrichment, carried forward through billions of years and countless stellar generations, eventually produced all the chemical complexity required for life. We're not just made of star stuff in some poetic abstract sense. We are the direct physical product of a chemical evolution that Webb is now tracing back to its earliest chapters. When you look at Webb's images of ancient galaxies, you are, in a very real sense, looking at your own origin story. But there is something even deeper than the chemistry, and it has to do with consciousness itself. The universe spent nearly 10 billion years building the raw materials, forging elements in stellar cores, scattering them through supernovae, assembling them into planets, nurturing the slow chemical evolution of life across geological timescales. And then, in the last cosmic eye blink, it produced something new, something that had never existed before in the 13.8 billion year history of the cosmos. A mind capable of looking back at all of it and asking how it happened. That is what we are. We are not passive observers of the universe. We are the universe's own capacity for self-reflection, made flesh, made mind, made curiosity. The atoms that spent billions of years cycling through stellar furnaces and interstellar clouds have, in us, found a way to wonder about themselves. Carl Sagan put it beautifully when he said that we are a way for the cosmos to know itself. But Webb has given that idea new weight, because now we are not just knowing the cosmos in a general sense. We are knowing its specific history, its infancy, its first structures, its chemical evolution across nearly 14 billion years. We are reconstructing the story of how the universe went from a hot, smooth, featureless plasma to a place complex enough to contain golden mirrors and the minds that designed them. That reconstruction is not complete. It is not even close to complete. But it is underway, and it is real, and it is one of the most extraordinary things our species has ever attempted, to understand not just where we are but how we got here, all the way back to the first light. I think about the people who built Webb, the engineers who spent 30 years solving problems that had never been solved before, designing mechanisms that had to work perfectly in conditions no human could survive, for a mission whose scientific payoff was too distant and uncertain to promise to any funding committee with complete confidence. They did it anyway, because the question was worth it, because knowing the answer, or even part of the answer, to how the universe began and how it built the structures we inhabit was worth 30 years of work and $10 billion and the collective intellectual effort of thousands of human lives. That choice, to spend so much of our finite time and finite resources on a question with no immediate practical application, no guaranteed return, no survival benefit, is one of the most distinctly human things I can imagine. It is what separates us from every other thing we have ever discovered in the universe. Webb is teaching us that we are late arrivals in an old cosmos, that the universe was building extraordinary things for billions of years before our planet formed, and that the first chapter of cosmic history, the one Webb is now finally reading clearly, was more dramatic and more surprising than we knew. It is teaching us humility, not the humility of smallness, though we are small, the deeper humility of recognizing that reality is larger and stranger, and more complex than our models, and that the universe is under no obligation to be simple enough for us to understand it all at once. And it is teaching us something about our own improbable place in all of this, that we are here, that we are looking, that we are asking, and that the asking itself is a form of the universe knowing itself, one question at a time, one golden mirror at a time, at the edge of everything we can see. We have travelled a long way tonight, from the first moment of the universe to the edge of the observable cosmos, from the cosmic dark ages to the ignition of the first stars, from the impossibly ancient light of Jades GS 1.0 to the invisible architecture of dark matter and dark energy that shapes everything we can see. We have sat with the silence between the galaxies and the silence between the stars, and we have asked quietly and seriously whether any other mind in this vast and ancient cosmos has ever done what we're doing right now, looking up, wondering, refusing to accept the darkness as the final word. It has been a long journey, and I'm glad you stayed with me for all of it, because the place we have arrived at is not the end of the story. It is the most interesting part of the beginning. Let me tell you what I think is the single most astonishing fact in everything we have explored tonight. Not the size of the universe, though that is staggering. Not the age of the ancient galaxies, though that is almost beyond comprehension. The most astonishing fact is this: we found them, against all the odds of evolution and biology and the random contingency of history, a species of medium-sized primates on a small rocky planet around an ordinary star in one of 2 trillion galaxies, developed the mathematics to understand light, the engineering to build instruments of extraordinary sensitivity, the institutional patience to sustain a 30-year project through political changes and budget crises, and the slow grinding weight of uncertainty. And then sent a golden mirror 1,000,000 miles into the dark and used it to read the oldest light in the universe. We did that, not a civilization of vast resources and centuries of advanced science. Us, right now. In our first few thousand years of recorded history, our first few 100 years of modern science, our first few decades of space exploration. We are just beginning, and we have already reached the edge of time. Webb's discoveries about the early universe, the massive galaxies that should not exist, the ancient oxygen that rewrites our timeline of stellar evolution, the redshift records that push our observations back to within 300 million years of the Big Bang. These are not just technical results in scientific papers. They are chapters in the oldest and most important story there is, the story of how the universe came to be what it is, and how we came to be the kind of creatures who could ask that question. Every anomaly Webb finds in the early cosmos is an invitation to revise, to rethink, to build better theories and design better observations. The history of science is a history of exactly this process, of reality surprising us, of our models breaking, of the discomfort of not knowing giving birth to the next generation of understanding. Webb has given us a magnificent and productive surprise. What comes next belongs to the scientists and thinkers who will spend the next decades working out what it means. But tonight is not for the next decades. Tonight is for this moment, for the particular, irreplaceable experience of sitting in the quiet dark and letting the scale of the cosmos settle over you like something soft and heavy and true. The universe is 13.8 billion years old. It contains 2 trillion galaxies. It is expanding, accelerating, growing darker and emptier at its edges with every passing billion years. 95% of it is invisible to us, made of things we cannot directly detect. It began in conditions our equations cannot fully describe and will end in the far future, in a cold and silent dispersal that no mind may be present to witness. All of this is true, and also true is this: you are here, right now, in the middle of all of it, breathing, wondering, part of the universe that is noticing itself, one quiet night at a time. I want to say something about what it means to be small in a large universe, because I think we often get this backwards. We treat the immensity of the cosmos as a reason for humility in the diminishing sense, as evidence that we do not matter, that our lives are insignificant against the backdrop of billions of years and trillions of galaxies. But I do not think that is the right way to feel it. The universe spent 13.8 billion years building the conditions for you to exist. It forged the iron in your blood in stellar furnaces. It scattered the carbon of your cells across interstellar space. It assembled a planet with liquid water and a stable star and billions of years of biological evolution, all of which conspired to produce a creature capable of looking up at the night sky and feeling awe. You're not insignificant because the universe is large. You're extraordinary precisely because the universe is large, and because from all of that vast and largely empty space, you emerged. Aware, curious, alive. We are the universe noticing itself. That phrase is not a comfort offered to mask the scale of our smallness. It is a literal description of what is happening when you look up at the stars. The atoms in your eyes are made of the same stuff as the stars they are observing. The electrons firing in your brain as you process the wonder of the cosmos are made of particles that have existed since the first minutes after the Big Bang. When you feel awe at the scale of the universe is, through you, feeling awe at itself. When you wonder about the first galaxies, the cosmos is, through your wondering, coming to know its own beginning. That is not nothing. That is arguably one of the most remarkable things that has ever happened in 13.8 billion years of cosmic history. The universe looked at itself, and it found the view astonishing. Thank you for joining me tonight. Thank you for staying with me all the way to the edge of time and back. If this journey moved you, if it left you with that particular mixture of peace and wonder that the cosmos so reliably produces in the quiet dark, please take a moment to like this video or subscribe to the channel. It is a small thing, but it helps more curious minds find their way here, to this space, where the questions are large and the night is long and the universe is always, always worth exploring. And now, before you drift into sleep, I want to leave you with one last thought. Somewhere out there, 1,000,000 miles from Earth, a golden mirror is floating in the dark. It is cold. It is silent. It is turning its face toward the oldest light in the universe, collecting photons that have been traveling since before the Earth existed, reading messages written in the first fires of the cosmos. It is doing this right now as you close your eyes, as your breathing slows, as the questions of the day grow quiet and the mind begins its own journey into the dark. The universe is still out there, vast and ancient and full of things we have not yet found. The next time you look up at the night sky, remember that the light reaching your eyes is old, some of it ancient beyond imagining, and that somewhere in that darkness there are galaxies we have not named yet, burning with a light that